Today we will discuss some AC circuit parameters, and I will start with introducing and discussing impedance. What is the impedance? Before talking about the impedance, let's remember the Ohm's law for DC circuits or the circuits that only contain resistor. We know that the voltage is equal to IR. R is the resistance, and we know that R is a constant relating the voltage and the current in DC circuits. So resistance relates voltage and current. Okay, what if instead of a resistor we have capacitor and inductor? How we can apply Ohm's law in the circuits which include resistor, capacitor, and inductors in addition of the resistance. So the Ohm's law for AC circuits can be written in this form. The voltage is equal to ZI. Z is called impedance. Impedance Z is the proportionally constant relating the phasor voltage and the phasor current. We know that in AC circuits, voltage and current are represented in the phasor mode. So we can say impedance Z is the proportionally constant relating phasor voltage and phasor current. Okay, so let's see what are the values of Z for different elements. So far we know what is resistor, what is capacitor, and what is inductor. Let's see what are the impedances for these elements. First, for resistor. For resistor, of course, the resistance is R, and in the phasor, the ZR, the impedance of the resistor, is the same as resistance. So ZR is equal to R for the resistor. For the capacitor, with the capacitance of C, we know that the impedance of a capacitor is equal to 1 over j omega c, or we can say negative j over omega c, because we know that j is equal to negative 1 over j, so these two are equal, these two terms. What is omega? Omega is angular frequency, and C is the capacitance. So impedance of a capacitor is 1 over j omega c, or negative j over omega c. Inductor. For inductor, with the inductance of L, ZL is equal to j omega L. So now we can easily find the impedance of resistor, capacitor, and inductor. One thing which is important is that for the resistor, the impedance of resistor is independent from the frequency, because there is no frequency element in the impedance. But for the capacitor and inductor, the value of the impedance is changing by the frequency. So for each frequency, for each specific frequency, we have a different impedance. So it's not like a resistor. For a resistor, regardless of the frequency, we say that the resistance is 100 ohms. We don't care what is the frequency. The frequency from 0 to infinity, the resistance is always, for example, 100 ohms. But for the impedance of capacitor and inductor, these impedances are directly related to the frequency. By changing the frequency, these impedances change. So each impedance can be calculated by knowing the frequency, and any specific frequency has its own gives the like its own impedance for a capacitor or inductor. And one more thing, let's see what is the impedance of capacitor and inductor for DC signals. For DC signals, of course, we know that DC voltage or current has frequency of zero. Frequency of zero. So, of zero, so. So, omega is equal to zero for DC signals. Let's see what is the impedance of a capacitor in for DC signals is 1 over j omega c, which is equal to 1 over j 2 pi f c. By the way, we know that when omega is 0, omega is 2 pi f, so also f is equal to 0. So 1 over j omega c, so it's 1 over c, it's equal to infinity. So a capacitor acts like an open circuit for DC excitation, for DC circuits. So we can say a capacitor acts like an open circuit for DC excitation or DC signal. Yeah, it means that if we have a DC voltage source, and we connect it to a capacitor, this capacitor acts like an open circuit because the frequency is 0. If this is AC, depending to the frequency, the impedance varies. Okay, what about the inductor? ZL, we know that is equal to J omega L or J 2 pi f L, and if f or omega are 0, ZL is equal to 0. What does it mean? It means that an inductor acts like a short circuit. So an inductor acts like a short circuit for DC excitation. It means that if we have a DC voltage source and we connect it to an inductor, it's like we connected the DC voltage source to short circuit. Okay. Now that we learned and we know what is the impedance, we look to all elements in the same way. So we don't care if the element is capacitor, it's inductor, or it's resistor. We say this element has an impedance of X. Okay, so all of them, we show all of them with the same shape. So we can have a box like this and say this element is Z. So if it is if this one is a resistor, of course it's ZR. If it is a capacitor, it's ZC. If it's inductor, it's ZL. So we can show all AC elements with symbols Z, and of course with a rectangle shape, and Z means like this is an AC element. Okay, so now resistors, inductors, and capacitors. What if uh, these impedances or devices in series or parallel? Of course, we know how to find the equivalent resistance, equivalent capacitance, equivalent inductance for resistor, capacitor, and inductor. But what if we just represent the element with Z, regardless of its type? If it's any of those elements, we just represent it with Z. How we can find the equivalent resistance, equivalent impedance? Okay, so let's find equivalent impedance. Let's say we have the circuit here, which is connected to several impedances or several components, Z2 up to Zn, and we connected these devices in series. The title of this part is series equivalent, and voltage division. Okay, so if we have our components connected in series, of course we have a voltage across all of them, and there is a current going through entire circuits, and each element has a voltage across it. So V1, we have V2, and we have Vn. Now we can say KVL, we can write a KVL for this loop, and we can say V is equal to V1 plus V2 plus Vn. Instead of V, based on Ohm's law, instead of V, we can say it's equal to Z1I plus V2 is Z2I. We know that the current moving through all these elements is same and equal to I. So for all of them we use I because the current is same. Z2I plus Zni. Now we factor out I, so we will have Z1 plus Z2 plus Zni, and V is equal to Z1 plus Z2 plus Zni. And so if we look to here, so we can say V is equal to Z equivalent I. So it's multiplied. So Z equivalent is equal to Z1 plus Z2 plus up to Zn. Okay, so here is the Z equivalent for series. But one thing, the Z is impedance, and we know that this impedance is a complex number because it can be it can consist of different elements like inductor, resistor, and capacitor. Capacitor and inductor are imaginary numbers, and resistor is a real number. So the total Z, which is Z equivalent, is a complex number. So we can show this Z equivalent in the form of complex number. The real part, of course, is the resistance, and the imaginary part is like Jx. So we can say that for the real part, the real part of Z is called resistance, and imaginary part of Z, imaginary part, is called reactance. Okay, so uh, we should know that both resistance and reactance are expressed in ohms. So the unit is ohms. So we say both resistance and reactance are expressed in ohms. Okay. For passive circuits, so far all the circuits we learned are passive circuits. Later we will discuss the active circuits, like if you remember for DC circuit we had the active circuits which we call it like op amp. So here we have a passive circuit. For passive circuits, resistance is always positive. Resistance is always positive because it's the actual value of the resistor. But reactance can be either positive or negative. So let me just write it down. For passive circuits, resistance always positive, reactance can be positive or negative. Okay, if reactance, if X is positive, we call it inductive reactance. If X is negative, we call it capacitive reactance. Okay, why when X is greater than 0 we call it inductive reactance? Because imaginary part has J, always it has J, and we know that for inductor the impedance is J omega L. You see, omega is positive, L is positive, so imaginary part is positive. So if X is positive, omega L is positive, we know that the uh, reactance is inductive reactance. For capacitive reactance, we know that the capacitive reactance is negative J over omega C. Okay, this number is always negative. because this number is always negative. If X is negative, we know that the reactance is related to the capacitor. Okay, when we add these two, if in our circuit we have both inductor and capacitor and also resistor, so resistor gives like in the Z equivalent, the resistor has a real part of R which is always positive, and the inductor has j omega L, and the capacitor has negative j omega C. We add these two terms, so j times omega L minus 1 over omega C. Depending to the value of the inductance and the capacitance, this number can be positive or negative. So it depends to the value of the capacitor and inductor. So this number can be positive or negative. So whenever we have both capacitor and inductance, whichever has greater term determines the sign of the inductance. Okay, so it depends to the values of the resistor, the values of the capacitor and inductor. But if we have only one of them, so if we have only inductor, of course the reactance is positive. If we have only capacitor, so the reactance is negative. Okay, but when we have both of them, we add we calculate this value, and whichever is greater, the sign will be determined based on the values of the capacitor and inductor. Okay, so now that we know what is the equivalent reactance, it's time to discuss the voltage division of the circuits with like DC with AC elements. So voltage division. Okay, so voltage division, we know that the phasor voltage across each element can be calculated by Ohm's law. So if we have this circuit, this is the rest of the circuit, and let's say we have two elements. With values of impedances of Z1 and Z2. The voltage across both of them is V, and we want to find V2, for example, as a function of V. We know that phasor voltage across the kth element number k, is V sub k is equal to Z k over I. Okay, it's Zk over I. And in order to find the voltage, we say the voltage across, for example, let's say element number 2, this element, is equal to, by the way, when I say it's ZKI, I I want to do one more thing. If it's zki, so this one is I, okay? So instead of I want to replace the I with like the voltage over to equivalent impedances. So we can say Z sub k times I. Instead of I can say it's equal to V over Z equivalent. Okay, and now as a result, we can say V sub k is equal to Z sub k over Z equivalent times V. If those impedances are connected in a series, we can say V sub k is equal to Z sub k over Z1 plus Z2 plus Zk plus up to Zn times V. And here in our specific example, because we have only two elements, we can simply say V2 is equal to Z2 over Z1 plus Z2 times V. Okay, so for this circuit with two elements, we know that the voltage division is this form, and it is exactly same as the resistor's voltage division that we learned in 221. We know that the voltage across each element is like across each resistor is the value of the resistor over total resistances times V. So the same thing here. The voltage across each element is the value of that element over the total of elements times the voltage. Or for more than two elements, the voltage across element number k is the impedance of element number k over the total impedances times the voltage. Okay, so this one is the main formula for voltage division. Let's do solve one example here. Here we have an example. In the following circuit, we want to find few things. A, find phasor current I. B, solve for phasor voltage or voltages across each element. And part C, find waveform corresponding to the phasors. Okay, and here is the circuit. We have an AC voltage source with a resistor with a value of 50 ohms, a capacitor with the value of 100 microfarad, with inductor with a value of 25 millihenry, and the value of Vs is equal to 35 cosine of 1000 t. Okay, we want to solve this circuit. The first thing I want to tell you, 1 milli is 10 to the negative 3, 1 micro is 10 to the negative 6, 1 nano is 10 to the negative 9, 1 pico is 10 to the negative 12, and 1 femto is 10 to the negative 15. Okay, so we should know these numbers, these conversions. Now, part A says find phasor current I. Oh, by the way, current I is this current moving through entire circuit. In order to find current I, the first thing we need to do is writing these values of the elements and voltage source in phasor, because now there are in farad, Henry, ohms, and like waveform. Okay, in order to be able to solve this equation, the first step is converting all elements in phasor. Okay, first of all, we know that omega, the frequency, is 1000 from here. Frequency is 1000. What is ZR? What is the impedance of a resistor? We know that the impedance of the resistor is regardless, independent of frequency, and it's equal to R, and it is 50 ohms. So this is the ZR. What is ZC? ZC is equal to negative J over omega C. We see that the impedance of the capacitor is related and it's dependent to the frequency. So it's equal to negative J over 1000 times C, which is 10 micro, so 10 times 10 to the negative 6. It's equal to minus 100 minus J 100 ohm. Or we can say it's equal to 1 over J 100 ohm. There are say. Okay, we got ZC. Let's find the ZL. ZL is JL omega. J is J. L is 25 millihenry. So we say J 25 times 10 to the negative 3 times 1000, which is equal to J 25 ohms. And of course, the voltage source V is equal to the phasor. It's the phase and angle. So phase is 35 and the angle is 0. And this one is the phasor, and we also know the frequency is 1000. Now that we have these values, we can we redraw the circuit again with the phasor values. Okay, I'm going to draw the circuit again. Here is a voltage source. Here we have a resistor. We have capacitor. We have inductor. And but this time, instead of the time domain value, we apply the phasors. The voltage source is 35 with the angle of 0. The resistor has 50 ohm voltage, so voltage across it, so plus minus VR is 50. Plus minus VR with a value of 50. The resistor, the capacitor has a voltage of VC across it, and the value, the impedance of it is negative 100J. And for VL, the voltage across the inductor is VL. The value of the impedance is J25. And now we can simply find find I, because the current is same for all elements, and we can find R by Ohm's law. So we write KVL for this circuit. So we start from let's say a resistor. So we say 50I plus minus J100I plus J25I is equal to 35 with the angle of 0. We factor out I, so it is 50 minus J75, which is equal to 35 with the angle of 0. Here, let me show you something. Let me change my highlighter color. Okay, so you see, this one is Z equivalent. This one is Z equivalent. And if we look, we see that it's a complex number. And the real part of this complex number is the resistance, and imaginary part, which is negative 75. Negative 75 is a combination of these two. Okay, depending on which one is greater, the sign of this number will be determined based on that. So you see that for the capacitor we have negative 1, for the capacitor we have negative 100, and for the inductor we have 25, and it's the reason that we have the negative imaginary part. Okay, and so we can call this as a capacitive reactance, because the capacitor has a higher value compared to the inductor. And one more thing, we solved up to this point. If we change the frequency in our problem here, if we change the frequency, all these values will be changed. So these values are determined based on the existing frequency. So if the frequency changes, the values will be changed. Okay, and now let's continue to find phasor I, and I is equal to 35 with the angle of 0 over 50 minus J75. Okay, how we can find the answer? We want to divide two complex numbers. If you remember from like the complex number lecture, we know that in order to divide or multiply two complex numbers, we need to convert both of them in the polar form. But here numerator is in the polar form, but denominator is in rectangular form, so we need to convert the denominator in the form of a polar. And how we can do that? We already have the equations. We know that like R is equal to the square root of 15 square plus negative 75 square, which is equal to 90.1, and we know that theta is equal to arctangent of B over A, which is equal to negative 56.3 degree. So we apply these values in the denominator, and we will have 90.1 with the angle of negative 56.3. So now that we reach to this point, we can divide the amplitudes, magnitudes, and subtract the phases. So 35 over 90.1 is 0.388 with the angle of 0 minus 56.3, which is 56.3 amp. So this is the phasor current. So phasor current is 0.38 with the angle of 56. Okay, part B. Uh, for part B, we are supposed to solve the phasor voltage across each element. So it's easy. Part B is easy because part B. Let me. Okay, part B. We use Ohm's law for the resistor. For the resistor, we know that voltage across resistor is equal to the impedance of the resistor times the current. All of them should be in the like phasor. The ZR is 50 times 0.388 with the angle of 53.6, which is equal to 90.4 with angle of 56.3. Okay, before moving to the next element, which is the inductor, let me tell you one thing. Any real number, 50. If we want, we convert it to complex number, this real number. For the complex number, for the polar form, we can show it with the same magnitude with the angle of 0. And for rectangular form, we can show the real part plus j0. So any real number can be written in these two forms. Okay, so here when I have 50, I replace it with this polar form, so it becomes 50 with angle of 0 times 0.388 with the angle of 56.3. Now it's easy. I multiply the magnitudes, which gives 90.4, and I add the phases, which is 56.3. So in order to combine any real number with complex numbers, just consider the real number in one of these two forms. Okay, so let's move and find voltage across find the voltage across the inductor. VL of course is ZL times I. ZL was J25 times 0.388 with the angle of 56.3. Okay, again here we want to multiply these two numbers. So one thing, J25 in fact was 0 plus J25. It is 0 plus J25, and it is the rectangular form, so we need to convert it to the polar mode, and we use same like r equal to square root of x2 plus y2, and theta is equal to arctangent of negative arctangent of y over x. We can use the same like conversions to convert this value to a polar mode, which is equal to 25 with the angle of 90. Okay, so this one is one more one thing that we should know. And now we need to multiply these two terms, these two magnitudes, and add these two angles. Okay, so if we do that, the answer will be equal to 9.7 with the angle of 146.3 volts. Okay, so this one is like VL. And before moving to the capacitor, again, I want to show you some shortcuts. So I said that if the number is a real number, we can simply say it's like x with the angle of 0, or we can say it's x plus j0. If we have a number like xj, if we have xj, let me just write it. So here is the real, here is polar, and here is rectangular. If we have like jy, and we want to convert it to the polar, I already told you that we can use these equations, but there is a shortcut. J means 90 degree. J means 90 degree. So we can directly say that if we convert it to polar, the answer will be y with the angle of 90. If we have negative jy, okay, don't get confused with these x's, y. So there are just numbers, okay. I can put m, n, o, l, any just value. Jy, if we have negative jy, we want to convert it to the polar. Again, we can use this equation, but negative j is always negative 90 degree. Okay, so these are some useful shortcuts. If you have any number with the angle of 0, in fact it is a real number and it is a rectangular form of like this. If we have a number with only imaginary part, okay, of course it's not a real number, but if we want to convert it to the polar mode, we know that j is equal to 90 degree. And if we have negative j, it's imaginary number, of course there is no real number, and in order to convert it to the polar mode, we can say the angle of the number is negative 90. And here, so we can use these shortcuts to quickly convert these values from real, polar, and rectangular form to each other. And but if we have, for example, m with the angle of 47, and we want to convert it to rectangular form, definitely we have to go with these equations and find it. But for some specific values, there are some shortcuts. And of course, we have one more shortcut, which we say x with the angle of negative, not negative, x with the angle of 180, in fact is negative x. It is a real number with a value of negative x. Okay, so let's go ahead and find voltage across capacitor, VC. VC is the impedance of the capacitor times the current is equal to negative J100 times 0.388 with the angle of 56.3. And now as I mentioned, we can use this shortcut. Any like negative jy is the number with the angle of negative 90, so it is equal to 100 with the angle of negative 90 times 0.388 with the angle of 56.3, which is equal to 38.8 with the angle of negative 33.7. So this was a part B, which we have the values. Part C of the problem, once we find the waveform of this waveform of these voltages and currents. Okay, first of all these voltages and currents have the same frequency, and the frequency is 1000. Okay, so all of them have the same frequency. And no, so we know that the omega is 1000 for all of them, and now we want to convert them in the form of waveform. We have two methods. If you remember, we know that we write in the form of real part of e to the j theta, e to the j omega t, and find which is equal to VA, which is equal to VA cosine of omega t plus phi. This is one method, and the other method was just writing the equations directly from the phasor. So let me do both of them so you get the idea. So IT, we know what is the like the polar, the phasor I. Phasor I was equal to phasor I 0.38 with the angle of 56.3. So it is equal to the real part of 0.388 e to the j 56.3 e to the j 1000 t, which is equal to 0.388 cosine of 1000 t plus 56.3. So this one is I of t. Okay, but I told you that we can directly, by knowing by like having the information, the phasor information was I was equal 0.388 with the angle of 56.3, and the frequency we can directly write the time domain without writing this line. So how we know that I of t is equal to the amplitude 0.388 cosine of omega 1000 t plus angle. Okay, so both of them, this one and this one, are same. Okay, so we can just use this phasor like to find it directly as a shortcut, or we can write this equation based on Euler's formula to find the time domain signal. And the next time domain waveform is VR of t is equal, whenever we are on phasors, we write it like VR. But when we are talking in the waveform and time domain, we should add this parenthesis t. So it depends to the time, so it's time dependent. So VR of t is 19.4 cosine of 1000 t plus 56.3 volt. V C of t is equal to, let me just write it in this, find it in the other way. So by the other way, so it's the real part of 38.8 e to the j negative j 33.7 e to the j 1000 t which is equal to 38.8 cosine of 1000 t minus 33.7. So it is Vc of t, and finally VL of t, which I want you to do it yourself, and that's for like series equivalent and voltage division that we just discussed. Okay, and now I'm going to talk about parallel equivalent and current division. Okay, let me check if my lecture is being recorded. Yes. Okay, let's go back to. Okay, so now we want to talk about parallel equivalent and current division. Let's assume we have the circuit, and this circuit is connected to n components with Z1, Z2 up to Zn. Okay, and we want to find the equivalent impedance. The total voltage is V and the total current is I, and each element has a different current entering or passing through it because they are in parallel. We know that based on KCL, we know that I, the total current, is the algebraic sum of the current. So I1 plus I2 plus IN. And now we can just say I is equal to V over Z1 plus V over Z2 plus V over Zn. Because all these elements are in parallel, there is the same voltage across all of them. So we know that the voltage here is V, the voltage here is V, the voltage here is V. So the voltages are same because they are connected in parallel. So now we factor out V. We can say I is equal to 1 over Z1 plus 1 over Z2 plus up to 1 over ZNV. And if we say that I is equal to Z equivalent times V, we see that Z equivalent will be equal to this value. So, I is not equal to E, sorry. I is equal to 1 over Z equivalent times V, because V is equal to IZ, so I is equal to 1 over Z times V. Okay, so so we can say 1 over Z equivalent is equal to 1 over Z1 plus 1 over Z2 plus 1 over Zn. Okay, so it's the like a general equation for equivalent impedances which are connected in parallel, and like conductance. If you remember for resistors, we said that 1 over R is called the G, and we call it conductance. We have the same thing for impedances. We show it with capital Y, which you can say capital Y is equal to 1 over Z. Y is called admittance, which is like the opposite of impedance, and which is it will be equal to G plus J beta. J is the same conductance that we know and we learned from resistors, and beta is called susceptance. Okay, so both of these conductance and susceptance, both of them are expressed in unit of Siemens. So unit of Siemens, the same unit we use for showing the conductivity, which is the opposite of uh, resistance, and the symbol is capital S. Okay, so this is the admittance and the parallel equivalent of uh, components with different impedances. So let's see how we can find the current division in AC circuits. So current division. Okay, current division, like as we did for voltage division, the current going through element number K is equal to 1 over the impedance of the element K over 1 over Z1 plus 1 over Z2 plus 1 over Zn times I. Okay, it's exactly like the resistors. So in order to find the current going through one element, we need to find this term and multiply it by total current to find the current going through one specific element. Okay, so now let's see one example for current division. Example, the following circuit is operating in sinusoidal steady state. Find, okay, A, find V, the phasor voltage. B, phasor current. Through each element. Part C, find waveform current. corresponding to the phasors, currents and voltage corresponding to phasors. And finally, part D, sketch phase diagram. Okay, now let's see the circuit. The original circuit is here. We have a current source in parallel with an with a capacitor with the value of 1 microfarad, and then parallel with a resistor with the value of 500 ohms, and an inductor with the value of zero point 0.5 Henry, and we here we have Is of t, which is equal to 50 cosine of 2000 t milliamp. Okay, so as usual, the first step is converting these values to phasor. We know that I will be equal to 50 with the angle of 0 milliamp. ZR is ZR is 500 ohms. ZL is JL omega, which is equal to J 2000 times 0.5, which is equal to J 1000 ohm. ZC is equal to negative J over C omega, which is equal to negative J over 2000 times 10 to the negative 6, which is equal to negative J 500 ohms. And now that we have these values, let's draw the circuit with the phasors. So here we have the current source, which has a value of 0.05 amp with an angle of 0 amp. We have a capacitor with a value of negative J 500. We have a resistor with a value of 500, and we have an inductor with a value of J 1000. Okay, and this one is the circuit. Now we want to find the currents moving through these elements. Let's see what we can do. The first thing, let's give some label the current. So the current going through the capacitor, we call it I1, and the current going through resistor and inductor, we call it I2, and the voltage across a capacitor across the capacitor is equal to voltage across resistor and inductor, which is V. And now it's time to find I1. Of course, I1 is equal to I1 is equal to, here I want to use the shortcut. If you remember from 221, I said that in the in the circuits that we have a current source with two resistors, if you remember, with two resistors and a resistor R1, resistor R2, and I. In order to find I1 and I2, I said the shortcut is we can say I1 is equal to the other resistor over total resistors times the current. So this one is a shortcut for the current division. Of course, we can use this general equation, or if we have like two parallel branches, we can use this shortcut. And here, because we have two parallel branches, like 1, 2, one of them is, we can consider like one branch, the other one consider the second branch, and use this shortcut to find the current. Let's see. We can simply say I1 is equal to the other impedance, which is here, okay, which is here, 500 plus J1000 over total impedances, 500 plus J1000 minus J500 times the main current. Okay, so it is equal to, if we convert these numbers to polar form, it's 1118 with the angle of 63.4 over 707 with the angle of 45 multiplied by 0.05 with the angle of 0, which is equal to, so we only need to divide 1118 by 707 and then multiply by 0.07, and for the angles we need to add 63.4 and 0 and subtract it from 45. So I1 will be equal to 0.079 with the angle of 18.43. So this one is I1. I2 is the current. Let me just erase this highlight. I2 is the current going through this branch. So we say the current going through this branch is the other impedance divided by total impedances times the current. So we will have the other impedance, which is negative J500 over total impedances, which is 500 plus J1000 minus J500 times total current, which is 0.05 with the angle of 0. We need to convert these values to polar form. If we do, we will have 500 with the angle of negative 90. Don't forget that I used the shortcut to convert this numerator to here. I said that the negative j is negative 90, if you remember. Over 707 with the angle of 45 times 0.05 with the angle of 0, which is equal to I2 is equal to 0.035 with the angle of negative 135. So this one is I2. So we got I1 and we got I2. Now that we have I1 and I2, let's find the V. So finding V is easy. We can just multiply one of these I's with the impedances. So of course multiplying I1 by this value, it's easier than multiplying I2 by these values, because we know that the voltage across this branch is the same as voltage across this branch. So we need to multiply I1 by negative J500, or as I said, I2 by 500 plus J1000. Okay, both of them give the same result. So V is equal to, we can say it's equal to negative J500 negative J500 times I1, or we can say it's equal to 500 plus J1000 times I2, which is equal to, both of them are same, okay, which is equal to what is I1? I1 of it's not sorry, here I1 is 0.079 with the angle of, I forgot the angle, with the angle of 18.43. Okay, now it's better. So if we calculate any of these two values, the result will be equal to 39.7 with the angle of negative 71.9. Okay, so this one is the voltage. Okay, now that we got the voltage, next part, once we find the waveform corresponding to the phasors. Okay, let's do that. Let's do that. V of t, of course, is equal to, from here we know that the frequency is 2000, so we simply say it's 39.7 cosine of 2000 t minus 71.9. I1 of t is equal to point 0.079 cosine of 2000 t plus 18.43 amp, not the first one is the voltage, and I2 of t of course is equal to 0.035 cosine of 2000 t minus 135 amp. So we got all waveforms, and the last step of the problem says sketch a phasor diagram. So in order to sketch the phasor diagram, we just draw the complex number plane. So we have real parts here and imaginary part in vertical axis, which is J. So and we can say I is here. It's not I. V. Yeah, V. V is here with the angle of with the value of 39.7 and the angle of negative 71.6. I1 is here. I1 is here. This one I1, this one is V. I1 with the like amplitude of 0.79 and the angle of 18.43, and I2 is here with the amplitude of 0.035 and angle of negative 135. Okay, and in the next lecture I will talk about more techniques to analyze AC circuits.